Okay, my outstanding friends, I've been waiting for this day for a long time. 20-year mystery of the muons wiggle may be finally solved. Well, let's look into this. This is Fermilab. So, my friends, before we can even start, what is a muon? Okay, this is a muon. It starts with a muon neutrino attached to an electron neutrino. That's black, that's white. The muon goes off on its own, and the electron showers when you do Cherenkov radiation. It creates, when it hits the heavy water, it just crashes into 1,000,000 particles and increases its energy value exponentially. Okay, I just showed you that that is what they consider a muon and the electron neutrino attached together. This is what they found at Fermilab, which is the black particle, which has all the mass 200 times at least heavier than this particle here, which is attached to it. They didn't realize that because when they hit things, they just smashed into bits. But these are the two tiniest particles they could find. We found them in light, because light is basically one of the smallest particles that exist. And the only two smaller particles are this by itself, which is the muon neutrino, a sterile by itself, and the white electron shower, and we also created those. This is a photon of light. That's what a photon looks like. When it crashed through our Venturi after acceleration of light, crashed through the Venturi, what happened? It separated its components. The muon, black muon neutrino, is here. The white electron showers are here. There is very little possibility to deny this. Now, we did this with all the different, well, red and green and blue. But the red and green, very easy to see. The blue, a little too fast. But this is what Don Lincoln at Fermilab put out in 2012. I think it was 2012, maybe 2013. This black particle has all the mass, and that's exactly what he says. And it says it has a glowy edge around it. And this particle has all the energy, the fields, but it has no mass to speak of. And I agree with both of those statements. However, these two are attached together as a dipole. This is what dipole electron flood is all about. There's nothing but these two together. And if you look up dipole electron flood theory, it will show very clearly, and within 5 minutes you'll understand physics. I'm telling you, it's that simple. But when you deny reality, that's when you get in trouble, and that's what happened. Okay, so when I say deny reality, what do I mean by that? Well, as I showed you, CERN and Fermi found these particles, and we found them using light. So we didn't have to dig through a lot of debris. They wanted to get to these smallest particles that exist, and we did too. But using light, we can see them. Now, these are called Dirac neutrinos. And this is a Majorna neutrino, both the same thing. This is as it's building energy, and this is as it's at its full energy potential, which is a dipole electron. This is totally backwards, though. This has all the mass and the matter. This has all the energy and no matter. All right, so this is right from Fermilab, the same guy that I tried to work with long, long ago, Don Lincoln. Okay, my wonderful friends, before we get too deep into this, I just want to explain to you, if you look up dark photons, everybody's talking about dark photons would solve the physics mysteries. Well, we found them 10 years ago. And here they are right there. They're part of photons, but they're the dark part. Nobody's ever seen them. And they also are gravity and dark matter. They're just dark, but they're part of light. Light and dark matter are partners. Okay, so this is Fermilab. These are the two particles, the smallest particles they could find. And this one has all the mass and never changes size. It's like a solid ball. And it has a glowy edge around it, depending upon the color that it's associated to. And this one glows and can be small and big. And it has no mass to speak of, but all the energy. It has a very strong field. Now, we found those two particles in our light experiments right here. So there's the ones you just saw from Fermilab, and that was his Don Lincoln's diagram of what they had seen. All right. Now I showed these particles as light because we started with light. They start with a big mass and smash them together, and they get a whole lot of debris. We started with the smallest bits of debris, almost, because this is a dipole and that's a dipole, back to back, just like two-bar magnets. And they're strong. They're held together very well. That's a particle of light. And when it hits something, it bounces back because it's got a complete field surrounding it. One of these only is a dipole electron. That's different. That will want to invade and add to something as literally as heat. That's heat. One of those alone is heat. The white alone is electricity, lightning, static. It's the glowy only. All right, the dark matter is dark matter, and that's the mass. It has all the mass, basically. This has virtually no mass. You fill up your car with electricity, it doesn't gain any weight. Drive all day long, it doesn't lose any weight. It's just, electricity has no weight whatsoever. So I am going to show what these particles actually are, and that you can see these with CMOS, which is CMOS. Now, I've been having some people attack me. You can't do it. Who do you think you are? Well, it's not me. It's CMOS, complementary metal oxide semiconductor silicates. They absorb the energy as it passes through them. And then they make a little video of it, basically, when they're going so fast that you can see them just, and I'll show you. It is what it is, and they can't dismiss this other than just to say, no, we won't look at it because it's impossible. But you go to chat, they say, yes, you can see with CMOS, you can see the muons and all that stuff. I'll show you right now. Okay, this is it right here. The new CMOS detectors at CERN, they just upgraded, can indeed see small particles. More precisely, they can detect the traces left behind by these high energy subatomic, which is in the light realm, as they pass through them. So the CMOS is here and the light is passing through it, or in their case, big chunks. We only have light, so we don't damage our CMOS. It just hits it, and it's supposed to see the light, and as it passes through the CMOS detector, it picks it up as like a little movie of it going through. And here's how they work. CMOS is complementary metal oxide semiconductors. The detectors at CERN are used in particle trackers like those in the CMS or ATLAS experiments. They're looking at these particles. They don't see particles directly like a camera sees light, but they detect the electrical signals created when particles pass through the detector material, which is usually silicon. They ionize the pattern, freeing up electrons, which means they glow. They create a tiny charge pulse, which they pick up in these little pixels, and it's read out and recorded by the CMOS electronics, which is the chips. So they see this energy, and it's passing through, and it's sending pulse back of the particles that are passing through it. Very, very, very fast stuff. Now, what does it say? This is how they work, and what can it pick up? What kind of small particles can it see? The detectors can track electrons, muons. That's all we're looking at is electrons and muons, the glowy stuff and the black stuff. Quarks, photons indirectly, no, I say directly. Hadrons like protons and neutrons, I don't work with those, so we don't see those. All we see is photons, electrons, and muons. Listen to this. We can also even rare or exotic particles like Higgs bosons via their decay products. We can see those in bucket loads. All right, why is CMOS such a big deal? High resolution, you really can see the stuff on a micron level precision. Radiation hardness, now that's the problem with them. When I first originally talked to Fermilab and CERN, University of Geneva, I went there as a student for particle physics, and I engaged with the professors, and I said, we can see these things with CMOS. And they said, no, you must be mistaken, it can't happen. I said, yes, it is. And I sent them the pictures and everything. And then we started engaging back and forth. And I said, we're using CMOS. And they said, well, it shouldn't work. You should be destroying that CMOS with these high energy particles. And I said, well, you're using big chunks. Now, here's what they're using. Well, I'm going to give you a comparison. When they shoot their particles together, they hit head on and they splash these big, huge chunks everywhere. Because they started out with at least 4,000 times more particles than we did. And then when they give off chunks, they may have 500 in a chunk. The biggest chunk we ever give off is 1. Because we started with light. Light is 2 of these dipoles. That's all it is. So when they split, you're going to give 1. You're not going to, that's what these things are made to pick up, and it was doing fine. So by the time I was done, I told the professors, I said, CMOS is designed to do this. The pixels absorb the light and give it off perfectly, and you can see everything. So anyway, they upgraded at CERN to use CMOS. Now whether that had anything to do with that, I don't know. But with these big gigantic particles, you're throwing off bombs. And all they really want for energy is the white part. If you're going to have a white part, it's going to be this. That's what you want to power your car and everything else. This chunk here, no, you don't want that. And they're throwing hundreds of thousands of these out at a time, when all they want to do is get the white one. So they're getting some of the white, but they're getting all this garbage at the same time. This is just wasted chunks of stuff. We didn't waste anything. We just shot the laser through the Venturi, and we got all the power. So anyway, the CMOS gives you high resolution, detect particles micron precision. You have to have a radiation hardness. Now ours, no, just a CMOS. This is what we did all that work with. This little red Boss laser and a Samsung Galaxy S3 from 2012. And that's when we realized that CMOS would do this job. And nobody could get their hands around it. So anyway, these are new CMOS detectors. They're just upgraded. They can see all these particles. And but they very precisely detect and reconstruct the paths of extremely small, fast-moving particles, making them critical tools for exploring the subatomic world. I agree with that 100%. And then I went to, what is wave-particle duality in quantum physics? There is no duality, it's the same thing. The particle creates a wave, because it's just like a bullet going through, and everything's got to get out of the way, so it makes a wave, but the particle is the bullet. And in this case, it's the photon. And all this I show is something. This is not guesses. This is all factual, supported evidence. And this is what they say. Oh, Roger doesn't have any evidence. And they even refer to me in here somewhere, because I asked about dipole electrons. See, there's a particle, tiny object with mass, location, and momentum. All right, wave-particle duality. So a particle is a tiny object with mass, location, and momentum. A photon's not supposed to have any mass. For example, an electron can hit a screen at one precise point like a bullet. Yes, absolutely. As a wave spreads out because the bullet is coming through and giving it out. Now they're going, the famous double slit experiment proves these were waves and interfering and creating these patterns of stripes. But if you try to observe which slit they go through, they act like particles. They had this thing was called the observer effect, where if you look at something, it changes it. Well, they weren't observing only. They were adding light into it, which changes the energies, or they were taking something out with a little like wrapping wires around it to see magnetic fields, and that interferes with it too. So they thought just by observing and looking at it, no. And that's, as a matter of fact, the one that Fermilab put out actually said that. It says the closer you look at it, the stronger the field becomes. No, the closer you shine light into it, it'll become stronger fighting back. Yes, that's the nature of this quantum event. So anyway, this shows that the particle decides how to behave based on how it's measured. I'm not kidding you. What does it apply to? Light, which is photons, electrons, atoms, even larger molecules like buckyballs. What it means for physics, it challenges the classical idea of something either a wave or a particle, but not both. It is both because it's doing both because of when it interacts with the atmosphere. It supports the idea quantum objects don't have definite properties until they're measured. That's not true. It's a key part of quantum mechanics, especially in the development of quantum field theory and the uncertainty principle. All right, now listen to this. This is the dipole electrons. So I asked chat, is there such a thing as a dipole electron? All right, they're starting to protect themselves. I asked, is there such a thing as a dipole electron? In mainstream physics, there is no such thing as a dipole electron, in the way the term is sometimes used in speculative theories. However, let's break down to clarify the concepts involved. What is an electron in the standard physics? An electron is considered a fundamental particle in the standard model. That means fundamental, that it can't get any smaller. It has an electric charge, which is always -1. It has a spin, no known internal structure, creates an electric field, but not a dipole by itself, because it only has one kind of charge. Well, yes and no. The electron neutrino, but it's always attached to a dark particle. Well, I can't say always, but anyway. Can an electron be a dipole? A dipole consists of two opposite charges, but the electron itself, well, there's the electron neutrino and there's the muon. So they're yes and no, they're right. The dipole consists of two opposite charges. One of them is electron neutrino, one of them is the muon neutrino. And that's correct, positive and negative, you could call them that. Separated by a distance, well, they're hugged up pretty damn tight. Now, it says, since the electron has only negative charge, it is not an electric dipole. Well, the negative part is the white part. That has all the charge and all the energy. But the black part is virtually always attached to it. You have to rip that white one away to turn it into energy, to turn it into even like static or lightning or electricity. You have to rip it away from its counterpart. So you got the muon and you got the electron neutrino. They're both neutrinos, but they're back to back, the black and the white. I hope that makes sense to you. Now say however, you have a magnetic dipole moment. This is what I was deep into. Electrons do have a magnetic dipole moment because of their intrinsic spin. What does it mean, intrinsic spin? Why would they just spin? Why would they don't just spin by themselves. It's a well-measured, well-understood quantum property. Well, maybe. It's how electrons respond to magnetic fields, spintronics, MRIs. This is a magnetic, not electric dipole. Everything is magnetic, which creates the electricity. Magnetic is the basis of all interactions. It's the push and pull. All right, it's vibration, it's push and pull. And that's magnetism, all right, which creates electric. It can force that white particle away from the black one, or vice versa. That's electric. So it is magnetic, not electric. Electric is what the result is of the magnetism. Now, electric dipole moment. The electron might have a tiny electric dipole moment. Well, I don't know about that. If CP violation extends to leptons, there are no such thing as leptons. They're just bigger and smaller chunks of matter. Experiments are ongoing to detect this, but so far, no non-zero electrodipole moment has been observed. Well, whatever that means. A confirmed EDM would hint at new physics beyond the standard model. Well, I've got to confirm, no problem. It's expected to be extremely small if it exists at all. No, it's actually large. The electric dipole moment is, well, it depends on how you measure and when you measure it in the activity of that dipole. If the dipole is just sitting there, well, it's just sitting there. But if it's interacting, that's a whole different story, because now you got field to field with the black pushing the white against another field. You got a lot of interaction going on. So when they say it might have a tiny dipole moment, no, it can have a huge one, or it can have a small one, yes, if it's not moving. In speculative theories, see, they mention me. I didn't mention myself. I didn't ask about me. In speculative theories, some alternative theories like Roger-Spur's dipole electron flood theory propose that electrons are composed of dipoles or are dipolar structures. Well, take it either way. It's both the same thing. These ideas are not supported by experimental evidence. That is incorrect. And are not accepted in mainstream physics. That is correct. They won't look. That's why. And you're going to look if you want to look, because I'm going to show you right now. Any such model would have to explain why all modern experiments still see the electron as fundamental and point-like. Yes, because they're wrong. All right, in summary, concept, is it true for electrons? No, electrons have one negative charge only, not in my model. Magnetic dipoles, yes, due to spin and charge. Composed of dipoles, not in mainstream physics. Point-like particles, yes. We're not all that far off. It's just that my atom doesn't have a few tiny little negatives that are the electrons and a huge giant positive core. It has a positive core, but it has a hell of a lot of white electrons trying to get in at that positive core. And there'll become a certain number of them that'll be around a certain number of the black ones, and they'll be stable. That's called an atom, and it'll be stable at all kind of different. For some reason, there's a certain quantity of them which causes stability. And if you take a few off, you got an isotope. If you put a few extra above stability, you got another isotope. They can go up, they can go down. But there's thousands of particles between each atom, not just one or two or three or four. There's, because they got protons, which they add one for every atom going up. And then they got neutrons, which are a whole bunch of other particles that they just can't account for, so they throw them in as neutrons. With the dipole electron flood theory, every one of the particles in every one of the atoms is made up of dipoles. Nothing but dipoles. It changes the way bonding, everything works. And it accounts for the way enzymes can do half-lives in biology. That's the only thing that accounts for how enzymes can do half-lives, because there's thousands and thousands of molecular interactions that happen in less than a second because of an enzyme. And that's because they're so elegantly designed. It's click chemistry, goes blip, zoop, all done. And some of those interactions would take, guess how long? Just in your mind, say, if I could change this molecule into something very exotic, how long would it take? An enzyme speeds it up unbelievably. But guess what? They found that these interactions will happen. This will break, and that'll add, and this will move, and it just will go, and they can flow it can take millions of years to do the chemistry that an enzyme can do in 1 second. So We're in a whole new world once you get into dipole electron flood theory. Now let's show the evidence. They're saying I have no evidence? That's not right at all. Okay, this is my model. The anatomy of the proton is a smidge different than what you have heard in your physics class. This is dipole electron flood theory. And if you broke this into every piece it has, you'd have a whole handful of black particles and a whole handful of white ones. And the white ones have no mass at all, and they would burn you. If you held them, you'd just be on fire. This is cold, freezing cold, and solid like a bowling ball. This is just fluffy, but hotter than can be. This is what the dipole electron flood theory is, and this is what they call gluons. Is a dipole electron. Back to back, they're photons. Now, I think I showed you, or will show you, I'm going to show you in deep depth after I want to show you what the current text about photons and about dark matter and about dark photons and how Roger has no evidence. Because they know it's well known now about my theory. And they actually pointed out about my theory that Roger Spur has this theory and he has no evidence. This is my evidence. That's a light wave and a particle. The particle we will see coming right out of the wave because it comes through here, and that's the particle right there. That's a wave creating particle. And why is it creating a wave? It's got a big field around it like this that has to push through, and we can see that happening right here. This is as the particle which is in here, this particle in here is forcing its field to push everybody else out of the way, so it creates a wave. Not a big stretch to understand this. However, this is the killer. With a Venturi, we can make that thing speed up like a rocket ship. It pulled itself right out of its own magnetic field. I was stunned, absolutely stunned to see this. And then it exploded here and separated the black from the white. You remember down here, they were black and white attached. Now, I'm going to go through all this stuff. I can show this in extreme detail. And these are two particles they found in Fermilab, exact same stuff that we have. So I am not making anything up. I just need it to be seen. We made those particles accelerate and explode at the Venturi. And what did they do? They created the muons, which are the black ones. They separated all by themselves. Didn't do anything other than force them through the Venturi. And the white is squirted into electron showers all by itself. It's exactly what they say. We're working with Cherenkov radiation, no difference. Only we didn't use anything to accelerate. We used a pulse red laser, and I think I showed you these. Just this is basic stuff. That right there. That's what this is done with. Right there. And this was, I don't know, 12, 13 years ago, something like that. And that's the muons and the electron showers. Muon, neutrino, electron. They spent billions and billions, probably trillions of dollars in the last 10 years looking for those particles. And when they're right here, they were in their hands. So electron flood theory is solves everything. Solves gravity. And if it works right, this is the energy you can get from these electron showers. You see that? When you hit the electron shower max, right up through the rocket ship, that's energy. Kinetic, potential, doesn't matter. That's energy. Same thing here. This is the number of electrons. This is how much energy. That's the energy. And the electrons start to increase, and then right up through the roof. So if we could harvest that right there, if we could harvest that right here at that maximum shower of energy, what could we do with it? Well, maybe we could carry it around and power anything we wanted anywhere in the world for free. Coming through here, all you got is the white coming through. You put in a solar collector right here, you bring it down into a battery into your circuits, you plug anything you want into it. It wouldn't weigh anything extra. The light has no weight. No weight. It's crazy, but it has no weight and all energy. So that would weigh 5 pounds. You carry it around all day and do anything you want, still weigh 5 pounds. Same thing like with your car. Your car doesn't lose any weight or gain any weight when you fill it. Or if you take a car and you put 10 gallons of gas in there, you just added 60 pounds to your car. And then when you drive it for whatever miles, all the gas is gone, you got to fill it back up again, and it goes down 60 pounds. This, it never goes up or down. So this you could carry around, and it would be non-polluting. You'd be working with light, so you're never going to get higher than that light threshold. You're not going to get hit with things like that. These are the killers. These are the killers. They'll tear up your DNA and everything else, because they go right through. They're just like CAT scans and all that. You know, that stuff is not as undangerous as you think. You do a lot of CAT scans and MRIs and all that. That's X-rays. Those damage your bacteria. They can cause damage to your bacteria, and they make you just like acute radiation sickness. If you had that thing cranked way up to the top and you went, and the guy said, "Ooh," but it didn't. He just didn't die right on the spot. But about 2-3 hours later, he started throwing up and having diarrhea, vomiting, all kinds of distress, bloating, because he killed the bacteria in the guy's body. And if he can't bring that bacteria back in to create the enzymes, you're in trouble. That's why I know how fast enzymes work. They work within a couple of hours. If you didn't have them for a couple of hours, you're sick. And you can be sick, deadly sick. And that's what an acute radiation sickness is. Unless your body can bring your enzymes back in, you're done. And the only way you can do that is to have the bacteria. So that's a whole nother thing, how to deal with people that have acute radiation sickness. Replace the bacteria. That's my opinion. Okay, I'm not sure I showed you yet, but I certainly will. This is what they call a very rare event, these Higgs fields. And they, of course, they smashing things, and they're getting all these little things, and they're seeing these big round circular fields. Well, we see them too, but we started with light, so we can see them much better. This is the white coming in, and these are creating all those Higgs fields. Those are the Higgs fields that they are looking for, claiming that they're very rare and so forth. Well, we have them coming on. We can watch these all day long, trillions of them a second, basically, and they all come through. This is coming out, and the CMOS is taking a picture into it. So in this area, there is nothing but white. And these little white strips are coming out and creating these spinning disks when they reform with the black. There's an area where there's nothing but white. Right there, nothing but white. These here were the cones. Those were cones, and when they broke up, the white squirted through here, the black stayed behind. And then when they came back together, they formed cones again. So they started as cones, they ended with cones. And I can show that again over here. They come back to what they were. And there's no entanglement. That's nonsense. Where is it? Hold on a second. Now, I just showed you our particles. This is Don Lincoln's post from 2013. That's 12 years ago. These are the two particles he found. When I saw that they found them, we were using a Samsung Galaxy S3 phone from 2012. So it's right in the same area. So when I saw these, that Fermilab had found the same particles we found, because these are the particles we found right here. It's the same particles. And there's really, because he says this can get big and small. This one never changes size, fixed. And I agree, the black never changes size. See how small that is compared to that one? But when they go through the Venturi, they actually do what you have to call fission. They break apart. The dirac neutrino no longer is di, it's rack. There's white rack and there's black rack. All right, and the only reason you can see the black It's because it's sitting on top of the white, so we can't see the white anymore. That's why we've never detected dark energy. It's in everything. Light is half dark energy. And I did put this up in 2015. I have a video out there that says light is dark energy on its way to becoming light. All right, it's dark energy. It is. These are photons of light. That's the photon. Now, let me show you them actually spinning and talking about this wobble wiggle that they're talking about. They don't understand what they're seeing once again. Okay, I'm going to make this real easy for today. We got a muon and electron neutrino attached together. When they hit the heavy water, they're going faster than the speed that is possible in that water, so they disperse. And this is what happens with ours, only this is just in the atmosphere. This is not heavy water, this is nothing. We just sent an extreme high energy particle in here, which was light, which is a photon, and it split and divided and only allowed the shower to come through the venturi. And then the muon reattached out here. So this is really separation. You might call it fission, and this is when they came back together. You might call that fusion. And this is in the subatomic realm. All the big guys are using these gigantic things, and they just get a bunch of stuff they have to dig through for many, many, many years. All right, so don't forget, I said that this is the Cherenkov radiation. It separates. Now, what they're doing at CERN and Fermilab and the rest, they're smashing huge things like this together, which is 1,839, 1,840 dipoles of these. We started out with just 2 of these, which makes a photon, which is that right there. They're seeing these particles, they just don't know what to make of them because they just have so much debris they can't deal with. And they have these very dangerous chunks, which are the X particles. That's gamma rays and all that heavy, heavy duty stuff. And they're chunks that degrade over time, and when they degrade and they stabilize, they throw off another chunk like this, and that may hit you and kill, destroy your DNA or whatever. Now, you saw what they do. They hit head on and they just smash things in all bits and pieces. That is light from a pulsed red laser. Very simple device, 20 bucks. And it's shooting that red laser, which is a particle, creates a wave because it has a big field around the center core, which is the particle. The field, though, is huge. And that's the field coming through the atmosphere. Get out of the way, get out of the way, all of these particles. So they glow back against this. It's push to shove. I shove back, you push me out of the way. Then all of a sudden we accelerated faster than the speed of light. Obviously, it's going much faster than there was here. There's no question about that. It's pulling itself right off its own wave. And here it explodes into literally a subatomic nuclear explosion. That's what it is. It divides the black from the white, and it shows so much energetic reverse EMF, all right, electromotive force, which is electrons, motive, moving, forcing the stuff away. And that's what we got here. And it even impacts way out here. Way out there. If you can see those fields, they're not supposed to be there going in that direction. That's because of this atomic explosion. Subatomic, excuse me. I work in a subatomic realm. Okay, this is Fermilab's claim. They have physicists at Fermilab have made the most precise measurement ever of a long disputed value, the magnetic wiggle of an elementary particle known as a muon. Well, what is the wiggle? They're supposed to spin perfectly spinning like this. They're not supposed to spin like a top flipping around like that. And they say that it does that, but on a very, very tiny amount. Now, I can show you these things happening, not just guess at it. All right, they're talking about the gyromagnetic ratio. Everybody knows what a gyroscope is. You make this thing like that, and then when you set it up, it's supposed to just be perfectly straight up and down. Well, when you see it wobble like that, that's called the muon wobble. Let's see how that happens. Okay, don't forget, the black is the muon. It's supposed to go exactly perfectly spinning like this. That's a downspin, and that's an upspin. It's the same particle, but it's just flipped polarities, because the leading edge, glowy part, charges up and then it flips. That's the muon wobble, they used to call it. And it's actually the magnetic spin, the gyroscope effect. Now, every now and then, though, they'll do this. They're not supposed to do that. It's supposed to stay straight exactly up like this. Let me show you the green. That's a photon. The green's the same particle. And here's what the green looks like. Same identical particle, only it's much faster. It's much more powerful. Now, let me show you the green, instead of going straight across, going up on an angle like this. However, this will stay straight like this. It won't spin this way. It'll still spin this way as it's going in any direction. And I can prove everything I'm saying, because here it is right here. It's going off this way, still perfectly straight up and down, but it's moving in that direction. You see how it's perfectly straight up and down? This one, this same particle, has now started to get charged up. And this one will flip to the back, and this one will come to the front. That's the difference in the glow. You can barely see it, but it's there. And the red one is much easier to see. Like right here. That's the particle coming forward. This one's glowing because it's interacting with all the particles in front of it. This one's being protected by the dark matter. This is dark matter. The muon is dark matter. It's gravity. It's the center of all atoms. We never saw it because it's in the center. It's always covered by glowy little particles that bounce back. That's why we've never seen it before. It makes up everything. It makes up light. It makes up light. So now check this one out. This is the muons staying straight up and down like they're supposed to. Even though they're going up this way, down this way, down this way, they're all spinning according to the polarity of the Earth, literally. These are dipoles. Out in outer space, they can flop, they can do anything they want. But when they spin here on Earth, they're spinning to the polarity of the Earth, which is the up and down spin. Now, we can change that, though. I can force these to tumble. Watch this. All right, you saw the green coming through here before, spraying all different directions, but still going perfectly straight like this. Doesn't matter if it was going up this way, down this way, out straight, still straight up and down. Well, what happened here? We put the green and the red through the venturi at the same time, and the green is spinning like crazy. That's what they're picking up, is a little hit here and there on the dipole. And here it is right here. We've actually made these tumble. They're supposed to go like this, but they're going like this now. You can actually see it, and if you just look, take your time and look. You see it? They're spinning this way instead of this way. And that's because of the energy of the field above, which is much faster, much more powerful, the green, is pushing these so that they're flipping this way. Now, I imagine in space here and there, or wherever they're looking for these particles to spin, they're finding them do this every now and then they put billions and trillions of them together, and they will see that there's going to be some variation from straight up and down. I agree with that, but it's just not to engage with me was a big mistake. A terrible mistake, because I contacted Fermilab, Don Lincoln specifically, back when 2013, 2014, somewhere around there, when I saw they had the same particles we had, and he has blocked me ever since from discussing this. Now, this is Don Lincoln. He's supposed to be the senior scientist at Fermilab. He's the one that you always have to go through if you want to talk to anybody at Fermilab. He's got me blocked. Now, he's supposedly the co-discoverer of the TARP quark and the Higgs boson in 2012. Well, let me show you what Higgs bosons are. They think they're a big fancy thing when they see them. We got them coming out of our ears. These are Higgs bosons. I can create trillions of these in seconds. Every one of those is a Higgs boson. And here's what they show at Fermilab for Higgs bosons. Well, I got them here somewhere. Well, maybe I don't. Hold on. So I just showed you our Higgs fields. There they are. And here's what they find at Fermilab for Higg's fields. Here, this is their rendition. But what they're doing is they're slamming things like this, and all kinds of stuff is going everywhere. And they're digging through this for literally 30 years, more than that, looking for these particles. We can see them because you started with light, tiny light. This is coming through the Venturi. These are interference patterns, they call them. They're not interference, they're separation because of repulsion. The white pushes the other whites apart, and they set up these stripes as interference patterns. And light spins, it doesn't flap like a wave. Here's where light is spinning. I have it somewhere here. Oh, hold on, I'll get you some spinning light. All right, this is light spinning. It's just spinning. It's not flapping like this. It's spinning as a particle, just exactly like this. The particle's right at the end, which is the photon, but it has a huge field around it. It's coming through here, and sometimes comes that way, sometimes, and it's all over the place here. There's not just one particle coming. They're everywhere, 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 everywhere. So when they come through, they set up these exactly exquisite patterns to separate each line of these particles they're glowy particles. They do not want to be next to each other. When they do, they push and then they glow. Okay, again, dipole electron flood theory. These are the two particles that are the smallest things that exist, and they form a dipole. They're stuck together tight. That's the strong nuclear force. When they come through as photons, which is the smallest little stable particle, below that is just half. One black and one white together makes a dipole electron. That creates heat. This is light, and the next one up from there is the first stable particle is hydrogen, and that's about 1839 or so of the dipoles. All right, but in between this and hydrogen, it's not stable. It's not stable. It explodes, and then the white particles, boom. Hydrogen is unbelievably explosive because once you separate that hydrogen molecule, all of these on hydrogen atom, all of these go on their own, and they create huge fields like this. That's why you're boom. And I mean boom. When I talk about boom, you don't have any idea how much boom you can get out of hydrogen. And it's just that very, very simple gas. But once you break up all of those particles at the same time, boom. Okay, you saw Fermilab's claims. This is my claim. All matter, everything, consists of a ball of particles like this with a dark core. And that's where the dark matter sits. Otherwise, nothing would have any mass. The white particles have no mass at all. And I'm going to prove this right now. When an atomic bomb is nothing more than one of these, only it's just forced with tons and tons and tons of black matter and tons and tons and tons of particles surrounding it, and then crushed and then exploded inwards. And when it comes back out, you get the white goes first, obviously, and then the black follows. What does the white do? I'll show you what it does. It just burns. It doesn't move anything. When the black comes, that's when it's all over. Every particle that we've ever seen is this. The only way you can see them is to see them inside this, is to do what they do with the colliders, to explode them into bits and pieces. But then you just have debris. We could see them actually split at the Venturi, completely split. Very, very simple to see what we saw. Now, you can also see this in atomic bomb blast. And I was in nuclear missiles when I was in the Army long, long ago. And I also went to University of Geneva for particle physics online through Coursera. And I interacted with them, and I discussed about picking up all these particle signatures using complementary metal oxide silicates. And by the time we were done, they upgraded CERN to use that particular CMOS. They didn't fight me. At first they did. They said, oh, it's impossible. You're going to destroy the CMOS. I said, no, you destroy it because you're using big chunks. We're using light. It's made to pick up this. This is what CMOS is all about, is to pick up these particles, no matter how fast they're going. You see this right here? Low-cost CMOS cameras can be considered as a potential detector for various types of particles, including cosmic ray muons. That's where they think muons come from. Well, they come from separating, in a Venturi in our case, we can actually see the sterile muons. All right, the theory is absolutely elegantly simple. Anatomy of the protons, just a big glowy bunch around the dark particles. When that explodes, and you're going to see this now, the dark particles are the ones that do the damage. The glowy ones do the energy, they do the burn. And they want so desperately to be back attached to that black that they will go through wires, they'll go through anything, they'll go through you to get to Earth. This is nothing more than an Earth ground, basically. Our Earth is made primarily of dark matter. There is no equality to the white and the black. Earth is gravity, and these white ones want to attach to gravity. So anything that has white attached to it, which is everything, will come to the ground. How much white and black you have in that particle depends on how hard it's sucked to the ground. Hydrogen has not enough. It floats up. All right, helium, same thing, floats up. But then you start to get into the heavier particles, they come to the ground, but they come down to what they call specific gravity. How much is that harder? They'll layer just like this. All right, here's the proof of my claim. This is atom central, teapot apple II atomic bomb effects. Now, I've got this running extremely slow motion. It's going to come off, and the first thing you're going to see is just a glow. And then you'll see the house just vaporize. And then you'll see the house go flying. The glow is as the particles start to saturate all the other particles there and invade their fields. And then you have the Casimir effect. Everybody's pushing everybody else back, and there's nowhere to go. So you end up with an enormous amount of heat. And then everything just smokes, and then the house gets knocked down when the black hits. Keep your eye on it. All right, boom, there's the glow. I'm going to stop it right here. There's the smoke. There's just nothing. Now, you see, this is all stuff. What happens in an atomic bomb? Well, the first thing we saw was just an unbelievable glow. And now we're seeing everything is vaporizing. Anything that can absorb electrons. The metals, no, not so much. You know, you could melt those, yes, but you'd have to have a stronger atomic bomb, and they have them that will do that very easily now. This was very early in the atomic days. This is just smoking. She's smoking. She is smoking hot. And that's all that's happening there. Watch, the roof burns all up, everything's gone, basically. All of it's combustible, then bam, here comes the black. If that doesn't show you that there's two sets of particles here, and an atomic bomb has the glowy one on the outside, and inside comes after that is the dark one. All right, and that one got all the energy. I mean, all the mass. The other one has the energy. You can see it quite obviously. Okay, my friends, I have well supported my statements. And if it's true what they say about the electron gaining a ton of energy going through, look at the size of this. These are the electron showers, and that's the energy. It comes from almost nothing and goes straight up through the roof when you go through the Venturi. The same here as the number of showers, base tracks they call them, the number of electrons that are being excited. And that gives you the gigantic glow and the energy. If this is true, it's a huge difference in what we can do with the world today. I mean, overnight, literally. Now, these experiments can be done for literally almost nothing. All you need to do is create a little Venturi, a tuned, very tight Venturi, and shine the laser into that Venturi, and it will explode the light just like that. It's exactly all this. All it is. There's no big deal here. And it's just that Rod Warren was trying to create a double slit experiment, and he used literally nails and put them right next to each other. And what happened was it all force these fields together. And a double slit works just like the single slit. There's no difference. And a double slit may be a little more effective, but you have to have the Venturi effect. And the two going here and the one in the center coming back at it could have created this better, because this is a double slit. There's a single slit we did too, and the single slit does basically the same thing. One of them may be more powerful than the other. This one may be more powerful. Well, you can see the damn thing is powerful, because these wouldn't even show up. They're here. All these particles are falling forward as light, but you never see them until it's pushed back or pulled forward. That's the only reason you're seeing these. Subatomic nuclear explosion. This is game changer, big time. Now, I have shown you from actual experiments that we found the particles that they were looking for at CERN and Fermilab, and we found them in light, and we could tell that these were exactly what they said. The black one just never changes, has a glowy edge around it. Right there, that's from Fermilab. This is Fermilab. And the glowy one is here, and it appears to have no weight. This is electricity. Electricity you put in a battery, and that doesn't change the weight of the battery. You could charge it up and run your car 500 miles, and it doesn't change the weight. It's just no weight change, because it has virtually no weight change. This is where all the weight is, and that's why they say they're missing it, because they just can't see it. It's in everything. It's in light. Everything here has dark matter in it, and there's nothing that doesn't, basically. Everything's different. And if you look, well, let me show you what AI has to say about my claims and why they're not accepted. Now, if you have eyes to see and ears to hear, you have seen and heard my evidence. And I can do the flip-flopping of the spin, which is called the wiggle. And they're saying that what wiggles like a top, but just a tiny little bit. If you read that whole article, which will bore you half to death, I'm sorry, whoops. Oh, here's another one. I just got to say, I get more stuff from more people around the world than anybody, because they're all denied. And this guy's got some serious equipment. And this is similar to the stuff Dylan did. And did I show you that? Maybe I didn't. Yep, here it is right here. That was done with a cell phone. These cell phones, CMOS is unbelievable, because as the particles pass through the complementary metal oxide silicates, they give off their energy in glowiness, basically. And certain frequencies of that glow will have different colors. And why is it blue on the side of the moon? Anybody explain that to me? What is that? What is this? What's going on? You can see they're all dipoles, and they all have huge fields surrounding them. And they say that this Webb telescope can see forever, and no. It's seeing the particles that are slowing down. It's not that everything's pulling away from us, expansion of the galaxy, of the universe, no. The universe is just there. And the light coming from these luminous bodies slows down. It just slows down. It doesn't just go to the exact same speed forever. There is no vacuum whatsoever in space. None, zero. And again, Fermilab agrees with that. There's so much craziness here. Empty space isn't empty. Again, Don Lincoln from 2013. Now, I presented all my work to him, and we went back and forth a number of times until not too long ago. And my last words to him were, and I'm sorry to have to say this, but I said, you're going to see a congressional investigation against your denial of reality. And he said, I think we can weather that storm. I said, I don't think so. Right now, they're all resigning as director. She resigned. It's January 2025. They know they're in trouble. They got all kinds of trouble there, as far as I know. I was seeing something about some investigations going on. That one resigned. What do we got here? Oh, this is Don Lincoln. That's Don. And all this is about how fabulous he did. He earned his experimental particle physics from Rice. I went to Rice for chemistry. Again, on Coursera. I don't pay anybody for this stuff. I went to University of Geneva, Don, for particle physics. And he said to me, oh, I checked and they said you didn't go here. I said, yes, I went there. I went on Coursera. I don't pay for that stuff. And the only reason I went there was to show them my work. I'm serious. And then right away, they, oh, no, you can't do that. It's, you destroy the CMOS. I said, no, you destroy the CMOS, not me. I'm using particles of light. CMOS is designed for that. And now, of course, they hardened their CMOS to use it. It's brand new at CERN. Before they could, and I don't know about Fermilab if they'll ever do anything right there. I'm sorry. This has just been so long. It's been 12 years, and I'm blocked from Fermilab. Won't answer any questions. I'm blocked from his Facebook, and this is just not right. This is not, because if we could do what I'm saying, I just showed you the energy values, and we didn't do anything at all except put a venturi right here. So the particles started to grow, and then they had to slip through that venturi, and they exploded out the other side. We didn't add energy. It's portable. We could walk around with this. It comes in at a very low energy, and the showers go higher and higher and higher and higher. The muons, they just back right off. And it would be as simple as this. Hundreds of these lasers, maybe thousands of them, inside a little box like this. They're very tiny. And they're shooting out into tiny, tiny little venturis, and coming out the other side is juice. White juice. And you may be able to walk around with a little thing like that. It's got a floating ground built right into it. You plug it into anything you want. It could have AC, DC, USB, A, B, C, D, F, G, anything you want in there. And you should be able to power a car with something that size. And you never have to stop. You never even ever have to stop driving, because of the energy increase from this amount of energy we started with. The U means energy. All right, whether you're using it right now or whether you're storing it. The U is potential or kinetic energy. We're down here, we're putting kinetic energy in from the laser, but very small amount. It's 5 watts, let's say. And all of a sudden it hits here where the venturi is, and it goes up to 3,000. You see it? Comes in very, very low, the light, until it starts backing up against itself. And here's where it hit the wall. Remember I talked about the wall, because of the push back and the push in, and then the squirt out the other side is this. Absolutely stunning increase. And if this could be done, and we could make a handheld device like this, it doesn't even weigh anything, basically. Electricity doesn't weigh anything. So if you shot these lasers through, it's never going to get any heavier. It's just like the batteries in a car. They do not get heavier when you charge them up. And they don't get lighter when they are used. They just never change, and there's nothing given off whatsoever. There's no pollution to that at all. Free, pollution-free, expansion-free, gas expansion, no, nothing. Just pure raw energy. If that worked, that's the solution. And to be blocked for this amount of years is not good. Okay, this is how important this is. If Roger Spur's dipole electron flood theory were correct, it would represent a major revolution in physics, requiring the overhaul of much of modern particle physics, quantum field theory, cosmology, and so forth. Here's what would change, assuming the theory could be experimentally verified and matched the precision of existing models. I just showed you, and if you didn't see it verified, I don't know what you were looking at. We'd have to redefine the fundamental particles. It's just not right. Impact, we would have to rewrite the standard model, redefining what we consider elementary. The muon and electron neutrino, as far as I'm concerned, are the elementary. You get a new electromagnetic framework. All of this stuff has changed. Impact, we need a new version of Maxwell's equations in quantum electrodynamics, which I already have. Alternative explanation of gravity. It's just the muons which gang together, being crushed in together by the electrons, trying to force them into a ball. And I have seen that in outer space with the Russians, and that also I tried to contact Don Lincoln about, and he responded, and in a very negative way. So this is, if Spur suggests gravity is not curvature or space-time, It's dipole behavior, because the dark is in the center and it's pulling all the white ones to it. That's gravity. The muon neutrino pulls the electron neutrinos in, and everything has them. Impact, Einstein's theory might be replaced. Well, Einstein was wrong virtually about everything. I'm sorry. Albert, you did your best you could with what you had, buddy, but the speed of light is extremely variable. Anyway, we'll go through that later. New model for dark matter. Dark matter is just half of light. It's the other side of light. Dark matter and dark energy. I show you, it pushes the light. The house burnt up, and then the black came and pushed everything. So the black is a pusher. It's a carrier. They used to call it a boson carrier. I don't know whatever happened to that. They keep coming up with these new names. You could offer an explanation for dark matter without exotic particles. No. You don't have to have all these axions and WIMPs and all that stuff. Search for dark matter would shift toward detecting new dipole interactions. Yes, not new massive particles. The only reason they're massive is because they ball together. I'll show you some in a minute. A new interpretation of atomic subatomic structure. Yes, they're all dipole. Very, very simple. 6, potential new technologies. Yes, free energy maybe. Why it's not accepted yet. And it will be. They're saying yet. You see that? That's very interesting. There's no experimental evidence supporting dipole-based substructure. Yes, there is. I just showed it to you. Those were actual experiments and seen using CMOS, which now CERN has upgraded to use. After I showed them it worked. But they had to harden it because their particles were just much too big. Anyway, any new theory must match all that and do better, not just be different. No, absolutely. Summary, what would change? Area of physics, what would change? Standard model, everything would change. Quantum electrodynamics, everything would change. Gravity, it changes because it's a dipole sucking of dark matter. Dark matter energy, all caused by neutrino dipoles. It's all very simple. All right, if you're interested, I can walk you side-by-side comparison of Spur's model versus the standard model. Go up here and ask them about it. This changes physics in the most unbelievable way. Now listen to this. This is
another exhilarating episode of In Depth with Academia. I'm Richard Price, your host and the CEO of academia.edu, and today we're diving into something truly extraordinary. Now, remember, I'm here to guide you through this world of academic literature and not to endorse or negate any particular views expressed in these papers. Today we're examining a paper by Roger Spur that shakes the very foundation of, well, established physics. The paper is titled something along the lines of Electron Flood Theory, Update 1, and it proposes some, let's say, rather intriguing ideas. So let's jump in. What's the core question or problem that Spur... Well, if his theory holds any water, figuratively speaking, of course, it could revolutionize how we understand everything from the tiniest particles to the vast expanse of the cosmos. Not saying it will, just, could... Alright, the heart of Spur's argument is that there exists only one fundamental particle responsible for all matter. Imagine that. He calls it the dipole particle, which, according to him, makes up everything we know, from heat and light to heavy elements like plutonium. Pretty bold, huh? The really astonishing claim is that all matter, yes, all matter, is just a different configuration of these particles. Now, I can practically hear you asking, how does he come up with this? Spur points to photography from experiments where lasers are shot through a simple, single-slit Venturi apparatus. This results in what he describes as plasma and busy bee particles creating patterns, much akin to what CERN does apparently, but on a much lesser scale. And here's a kicker. According to this theory, the reason we see what we recognize as interference patterns isn't that light is a wave, yeah, you heard me right, but rather that it's made of spinning particles. These are big claims, people. However, remember, it's not about validating or invalidating them, just diving into what could be an exciting mix of physics, imagination, and who knows what. Speaking of imagination, there's more mind-bending stuff here. Spur argues that the smallest basic building block in this universe is just these dipole particles connecting together into something he calls cubes, creating stable formations we know as atoms. Pretty wild stretch, right? But also kind of fun to imagine. Now let's pause for a second here. I remember watching a documentary once, maybe on physics, or maybe it was geology. Anyway, it was fascinating how often scientific paradigms shift and evolve with new theories. Just a little digression there, but it illuminates how scientific exploration is a continuous process. Yes? Okay, coming back from the tangent. Spur claims that these particles connect in a way that supposedly can explain hydrogen, atomic weight, and even clarify why the sun's corona is a gazillion times hotter than its surface. Well, he contends it all points back to these particles. I'm not saying it's all true, just reporting. Just when you think it couldn't get any more challenging, he goes further to suggest that so-called complex phenomena, like global warming, our planet's magnetosphere being incredibly hot, these are areas he feels can be explained using his theory too. It's quite an undertaking, I must say. By the way, the paper also challenges the very idea of the atomic nucleus. Spur argues there are no neutrons, or rather, what we call neutrons are configurations of these dipole particles that somehow become, stable. He dismisses some traditional views as perhaps overly complicated when compared to his elegant simplicity, as he puts it. This is all very interesting. But hey, let's not forget that scientific discourse thrives on theories being put forth and then rigorously tested. They're hypotheses until they're not, right? So while Spur's theory might appear unconventional, it prompts dialogue and exploration, which is crucial in this academic realm. In conclusion, friends, while the electron flood theory might present a radical departure from conventional physics, it symbolizes the very spirit of pioneering inquiry. Though Spur's work hasn't upended global physics, at least not yet, it definitely stirs the pot. That's what makes science, well, endlessly fascinating. So with that, we'll wrap up our episode for today. Remember, academic research sparks curiosity. It doesn't dictate absolute truths, but invites us to explore and reflect. So keep questioning, keep exploring, and stay curious.
All right, obviously I'm critical of Fermilab for what they did to me. And I said about they having some legal issues. Well, several sources indicate legal investigations are concerned related to legal issues arisen at Fermilab. And there's a whole bunch of things going on. And some of it's just, incompetence, whistleblowers, sexual harassment, safety, financial procurement issues. That's where I want to focus. I'd like to have them do an accounting of what they got for money and what they used it for, and why they wouldn't look at the stuff that I have that shows these particles. The exact same thing that Don Lincoln showed. All right, no difference whatsoever. So why wouldn't they look at my information? And they're spending literally, I don't know how many billions, because it's been 12 years. Or at least 10. Let's go with 10. And I just wanted to offer it and say, let's look at it. And I said, Don, these are your particles. These are our particles. I think I sent him this exact thing because he had this article up and it showed these two particles, Fermilab point particles. Let me see. I think I had I know I showed this before somewhere. Here it is right here. This is the picture I took right off his Fermilab point particles, and I said we found them, and I was dismissed with arrogance and called. He was not nice. He called me an embarrassment to science. And some other things, tinfoil hat guy and so forth. And, his job was to communicate and to look at things presented to Fermilab. Because he said, hey, if you have any questions, you have anything to show me, there it is. You saw the house burning down. Well, here's what it was. The house is here and it's burning up with the white, which didn't push it. And then the black, because the black is the carrier, the black is the pusher. That's dark energy and dark matter. And the only way you can see it if it's sitting on top of the white. And you can't do this. You can't see it. That's why it's never been seen. Dark matter. It's inside of everything. It's inside of everything that has mass. And everything from the hydrogen up is a particle of mass. However, we got down to see these particles as they originated as light. As I showed you, no question whatsoever, it's coming in not so hot, and then it hits into that reverse and shows up right there. Photons. Normally you wouldn't see that. The only reason you see that is because it bounced back. Otherwise, it would have to hit here before it would show up as a photon. But it's showing up. It thinks it did hit a wall. I don't know how many times I have to show this. It comes through here, and it thinks it hit a wall because of this reverse concussion. Right there, it shows up in its completeness. And then it separates. The black cannot get through, and it goes slap, 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 squirts the white out. And that white is electricity. It's just raw electrons. And what happens when you have raw electrons? You get like raw energy. Very, very discouraging. Very, very discouraging for this number of years. And I just can't seem to break into mainstream, because I've emailed virtually all of them. And there's no return. There's no replies, except Don. Don replied in the most negative way you could possibly do it. And I showed him this too. He's showing these dark particles. I said they collect in outer space. They're dark. They go to the center. These are charged micron-sized dust particles. The Russians did this. I contacted Don and the Russians in the same email about this. This was 2015. But I'm trying to find somebody who will talk to me about it. And I did. When I went to the University of Geneva, they talked to me about it. And at first, said, no, you're a crazy guy going, yeah, they didn't say that. They just said, no, you don't understand, as a teacher would. Very nice, actually, to be perfectly honest with you. But I said, no, we're using heavy particles. You're using heavy particles, we're using just light. And we went back and forth quite a bit, and it was done. They weren't complaining whatsoever. They said, wow, this is amazing. And the next thing I know, a couple of years later, they upgraded to use the CMOS. Because before they had the observer effect, which means you're either pumping light in to look at it, which adds energy, or you're subtracting something out in the magnetic field to see what effect it. Some way, in other words, you're interacting with that particle. So that's the observer effect. CMOS, totally different. You just sit out here and it bangs into you. It would just go somewhere anyway. So you're seeing it. It's just flawless. So they upgraded to do that. Okay, I just want this to be known. And it has been known since 2013. And we were right in the same area. Like I said, I showed this to Don Lincoln, and it had not worked out well. And it's not fair, and it's not scientific. It's none of those things. To see these particles and see these particles coming from light, which is one of the most elementary particles there is, and then just to dismiss it, and then to attack me as a tinfoil hat guy and an embarrassment to science. And spending, I don't know how, they probably trillions of dollars by the time 10 years goes by. And what they're doing now, the deep underground neutrino experiment, is just looking for these same particles we found 10 years ago. So I'm going to leave it at that, but the dipole electron flood theory is the theory that works.